Welcome to Curiosity. Today we explore the last human alive, humanity's final epoch. It's a heavy title, I know, but stick with me because this explainer is going to take us on an incredible journey.
One day, somewhere in the unimaginably distant future, there will be a last human. One final heartbeat, one final thought, then humanity will be gone forever. Wow, it's a profound, almost heavy thought, isn't it? But look, understanding the eventual end of human existence isn't just an exercise in doom and gloom or nihilism. It's actually a scientific certainty, totally bound by the fundamental laws of physics. Whether we succumb to some near-term catastrophe or somehow persevere through billions of years of cosmic evolution, there will eventually be a final chapter. And by modeling these extreme long-term scenarios, astrophysicists and evolutionary biologists can actually test the absolute boundaries of our current scientific theories. Honestly, I think it sets an awe-inspiring, really contemplative tone for what we're looking at today.
Section 1. The Law of Entropy. To really understand our ultimate end, we first have to look at the fundamental physical laws that basically guarantee it.
And the big concept driving this whole thing? Entropy. It's rooted in the second law of thermodynamics. You've probably heard of it. This law states that total entropy, which is basically just a measure of disorder or unavailable energy in an isolated system, can never decrease over time. Think of the universe like a magnificent, incredibly grand clock that is just slowly, irreversibly winding down. Now, you and I, as living organisms, we're highly ordered low-entropy structures. We maintain our existence by consuming low-entropy energy, things like sunlight or the food we eat, and then we expel high-entropy waste, like heat. But here's the catch. When the universe eventually hits maximum entropy, all temperature differences will just cease to exist. And without a temperature gradient, no thermodynamic work can be extracted, which means biological processes become mathematically impossible. Period.
The exact mathematics behind this inevitable winding down are dictated by the Boltzmann entropy equation. Simply put, as cosmic time stretches out toward infinity, the universe literally must transition into a state of absolute maximum disorder. So what does that actually look like? Well, picture a uniform, totally diffuse, and completely lifeless bath of radiation. Scientists call this the heat death of the universe. It's kind of the ultimate cosmic flatline. Section 2. Earth's final eras. But hey, long before the entire cosmos goes dark, we really need to look closer to home to track the timeline of our own planet's limits. Assuming we manage to survive our own self-inflicted risks, which we'll definitely get to later, our demise will eventually be dictated by the Earth itself. The clock is ticking. In about 600 million years, our sun is going to grow brighter and hotter. And surprisingly, this extra heat accelerates the weathering of silicate rocks, which literally acts to trap carbon dioxide down deep in the Earth's crust. So as atmospheric CO2 plummets below the critical threshold that's required for C3 photosynthesis, plants are simply going to suffocate. And as you can probably guess, without plants, oxygen completely vanishes. Macroscopic animal life, and yes, that includes any human still hanging around, faces total extinction. Then, by the 1 billion year mark, the sun's luminosity will have increased by roughly 10%. The result? Global temperatures are going to hit a staggering average of 47 degrees Celsius. That's about 116 degrees Fahrenheit globally. This triggers what scientists call a runaway moist greenhouse effect. Water vapor is a super potent greenhouse gas, so it's going to trap even more heat in a vicious cycle. The oceans will rapidly evaporate, and ultimately, Earth's surface will become completely desiccated and totally sterile. Just a dry, baked rock. Let's fast forward even further, to 5.4 billion years from now. The sun will finally exhaust the hydrogen fuel in its core. This forces the core to contract and heat up, which ignites a shell of hydrogen fusion on the outside. This is what transforms our sun into a red giant. Its radius is going to expand up to an astonishing 256 times its current size. Mercury and Venus, they'll be completely engulfed and vaporized. Gone. And even if Earth's orbit somehow widens enough to avoid being physically swallowed by the sun, our planet's surface is going to be melted into a vast, glowing ocean of magma. It's truly an apocalyptic picture. Section 3. The Dark, Lifeless Cosmos. Having witnessed the fiery end of our solar system, let's zoom way out into the deep time of the cosmos, exploring the eras that await long, long after all the stars have burned out. Let's say our descendants actually manage to migrate to long-lived red dwarf stars in other systems. Well, eventually, even star formation ceases entirely. In about 100 trillion years, the very last star will burn out, bringing our current era, the stelliferous era, to a definitive close. From there, we enter the degenerate era. This is a cold, dark place populated only by white dwarfs, neutron stars, and black holes. Any surviving digitized human consciousnesses would face severe, crippling energy starvation. Then, in a future so distant it's hard to even wrap your head around 10 to the 40th power years from now, grand unified theories suggest that protons themselves might actually decay. If protons dissolve, all ordinary matter, meaning planets, dead stars, everything, just evaporates into a faint mist of radiation. I want to pause here for a second, just deliberately, to let the unimaginable weight of this number sink in. 10 to the 100th power years. That is a 1 followed by 100 zeros. We call this the black hole era because literally only supermassive black holes remain. But here's the thing. Thanks to Stephen Hawking's brilliant application of quantum mechanics, we know that even black holes aren't eternal. Over this absolutely staggering timescale, they emit a faint thermal signature known as Hawking radiation, and eventually even the absolute largest black holes in the universe will evaporate into a final silent shower of photons and gravitons. And what is the engine driving us toward this dark, empty expanse? Dark energy. Precise astrophysical measurements from the Planck satellite and the James Webb Space Telescope have confirmed that dark energy makes up approximately 68% of the universe's total mass energy density. This is crucial because it ensures that the expansion of the universe is not going to halt. It pretty much cements the big freeze scenario, where the universe just expands forever, slowly cooling down toward an infinite, lifeless void. Section 4 are immediate preventable threats. Okay, let's snap back dramatically from trillions of years in the far future right back to the present day. Because while long-term cosmology dictates our ultimate end, contemporary science warns us of some very immediate, human-caused risks. These are the self-inflicted threats that could actually bring about the last human alive within mere centuries, rather than billions of years. If you look at current literature in leading scientific journals, they heavily highlight this dangerous intersection of rapid technological advancement and human security. We are currently facing massive global catastrophic risks. We're talking runaway climate change, the looming shadow of nuclear winter, unaligned artificial general intelligence, and the incredibly tricky dual-use dilemma of engineered pathogens in modern virology. Let's look at one particularly alarming recent focus in the scientific community: synthetic biology. Specifically, there is this theoretical risk of something called mirror life. Here's how it works. Normal terrestrial biology relies entirely on specific chiral molecules, which are known as L-amino acids. But if we were to engineer organisms using their exact mirror image molecules called D-amino acids, they would have absolutely no natural predators. Think about that. They would be completely invisible to all known immune systems. If a mirror-life organism were accidentally or intentionally released, it could easily cause a rapid, completely unstoppable ecological collapse. It's a terrifying, very real possibility. Section 5, the value of now. And this brings us to the most vital takeaway of this entire explainer. Look, understanding the immense distant finality of the cosmos shouldn't just make us feel small, it should really inspire a profound appreciation for the present moment. The contrast here is just stark. On one hand, our biological deadline, driven by those inevitable natural planetary mechanisms like solar expansion, gives us a massive runway. We've got roughly 1 billion years. But on the other hand, the immediate threats, the ones driven by our own preventable human actions, those could end the human story within the next century. So the probability of human extinction in the near term, it's orders of magnitude higher than extinction from any natural astronomical phenomena. This realization underscores just how incredibly rare and valuable conscious life really is. The responsibility lies with the present generations to ensure that the human story is not cut tragically short by our own hand. Our current era, the stelliferous era, is this incredibly narrow, beautiful window in cosmic time where life is even physically possible. Protecting it is quite literally our greatest responsibility. The last human alive might one day stand on the desiccated plains of an expanding Earth, or maybe they'll exist as a digitized consciousness witnessing the last red dwarf star slowly fade out. But long before that distant horizon is reached, it is entirely up to us to navigate the present. So, I want to leave you with this final thought. Will we safeguard our brief window in cosmic time? Yes, the universe has a strictly defined expiration date, but our immediate future, it absolutely does not have to be written in tragedy. It's in our hands. Thank you so much for joining me on this exploration of the furthest reaches of time and bringing it right back to the urgent importance of today. See you next time.